Okay, the next step is I want to show you in chapter 2.3 the reduction methods of SBDs. What this is a reduction method. I want to show you that it is possible to change the signal block diagrams in that way that you can reduce the number of blocks to finally to one single block, and then you have the total gain of the system. For example, if you want to have the voltage gain of the operational amplifier circuit number 1, I show you a method where this can be combined to one block, and then you have the U2 over U1. If you want to have, for example, the voltage gain U2 over U1 of the circuit with the two RC blocks here, I show you a way where you can combine this complete structure to one single block, and then you have the voltage gain of this second order low pass filter. There are some methods which are simple, but there are also methods which are not so simple. So this chapter needs at least, I think, 2 videos to show you, and a third video to make some examples for this reduction methods of the signal block diagram. There are 3. First step is 3 simple methods to reduce number of blocks. One is simple. We assume that these blocks are given with a transfer function, so that we can say, okay, f, if this is x and this is y, can say y is simple, the complex transfer function value y of p is simple, the transfer function f of p times x of p. Or f is the you can say the gain of the block, f is the ratio of y of p divided by x of p. We talking about frequency functions, and then the output y is simply the product of transfer function and input value. This is of course not true in time depending signals. If I have here given the step response, and here I have a sinusoidal signal, I of course cannot multiply the step response with the sinusoidal function to get the output. Then the way to work is totally different. So this is only valid, and that's the reason why I want to use Laplace transformation, because then the combination of more than one block with other blocks is very easy to calculate. The first simple method is the series connection. Series connection of 2 blocks. Series connection means I have 2 blocks, namely first block with function f1, so this is x, I have output y, and then directly followed by a second block with a second function. And of course this connection is not, the input is not a load for the output. So this connection is easy without any interaction. That is very simple in that way. If they say I want now to combine those blocks, this is easy, because y is nothing else, y of p is here defined by our transfer function is f1 times x, then z is f2 times y. Now I replace this y here, and I can directly write z is the f2 times y, and y is f1 times x. So finally we have z is f1 times f2 times x. So this is a new function, new, and you see, yeah, if I combine the series connection of two blocks, the new result is I get one block out of these two blocks, where X is the input, Z is the output, where F, the total function, is the product of those single functions. Yeah, a series connection can be solved, can be reduced to one block by just filling the new one block with a product of F1 and F2. That is a series connection. Second simple reduction method is the parallel circuit. Parallel connection. That means the starting situation is I have two blocks. Here F1, second block F2. The inputs are connected. Input is X. So the both inputs of both blocks is X, and now I have an output. Say this is Y, and this is Z. So the question is, how can I combine now these output blocks signals? It is not allowed just to glue them together, to solder them together. It is not allowed because this is a contradiction. For example, if this is 1 ampere and this is 2 ampere, if I connect them, how large is then the total value? If I connect them, that is not possible. Yeah? If this is a battery of 12 volt and this is a battery of 24 volt, and I make a short circuit cable between both, then you will see there will be a very high current, and normally batteries will be destroyed. So this is not allowed to directly connect to outputs with a junction point. So the only possible connection in a signal block diagram is the outputs are combined together with a summing point. Yeah, and the summing point gives now the output, say A, and you can directly calculate A is Y plus Z. Of course, there is a minus sign allowed. Yeah, of course, each branch can have a minus sign and inverter, then this leads to a minus sign in the equation. So A is, and Y is F1 times X, 1 times X, and Z is F2 times X, 2 times X. You see, then the resulting function is F1 plus F2 times X. So this can be combined to a new single block parallel circuit with summing point for the output signals. X is input, A is output. A parallel structure is easily be reduced to one block by adding the transfer functions of the both single blocks. That is the second simple circuit, and the first simple circuit, which can be reduced to two blocks, can be reduced to one block, is the feedback loop. Yeah, parallel connection or feedback. Okay, this looks like the following. We have an input, summing point in the beginning, block number 1, F1, output, say this is X and this is Y. Okay, now output signal is connected with a branch, and this will be the input of a second block, which is backwards connected. This is F2, and the output of F2 now is connected to the second input of the summing point. Here we can have a negative sign, and you know, in parentheses I write this negative sign. I want to have the equation for positive and for negative feedback. So I want to have goal. Yeah, that's my resulting expected result is I have an input X and an output Y, and this should be the new function. This new function should be calculated. I know the new function fn is output y divided by input x. This is what I want to calculate, and this result can be used in my lecture later in many applications. Now that's the most important rule, the feedback rule in signal block diagrams. So note what happens now with my fn. How large is fn? You should learn this, keep it in mind, learn it by heart. What else? You will now get the most important equation in this lecture. First, if this is y, the output, I can directly calculate the f2 output, because the f2 is nothing else than y times f2. So this signal on this line is y times input, is f2 times input, so this is y times f2. The resulting signal here, the control difference, we can say, the control difference can be calculated using the summing point equation. Control difference is x plus or minus y times f2. And finally, you can say y is, this output is f1 times input, so y is f1 times xd. Now I replace control difference with the previous equation, so we have f1 times xd. xd is this, and this is x plus or in parentheses minus y of f2. And you see now that y on the left side has an f1x on the right side, but also a plus or negative sign y times f1 f2. This equation is useful to calculate this expression, because now this expression can be used. I need y on the left side. This is fn times x on the right side. Yeah, this is the same expression than this. So I have to bring this term on the left side, and here I have only y's, and here I have x, and then I can easily read how large is fn. Next step is y, and now you see if I bring this on the other side, this is a minus if there is a plus, and here is a plus if there is a minus. So this sign is the inverted sign of this feedback sign. Minus or plus y times f1 f2 is f1x, or I extract the y signal here, y1 minus or plus f1 f2 is f1x, and the final goal is y over x. Y over x is my searched function. Y divided by x is, now this parenthesis quantity has to be divided on both sides, and this is gone, and here we have f1 divided by 1 minus or plus f1 f2. This is my f nu. Now this is the most important equation in this lecture. So we can say, okay, the reduction of a feedback loop is x is the input, y is the output, and the new function within the new block is f1 in the numerator. That is the block we can find if you go from the original input directly to the original output here in this way. No, escape, come on, escape. No. F1 is that function you can find directly the connection between input and output. And in the denominator you always see a 1 here. followed by a sign, which is the opposite sign of the feedback sign. So I have a plus sign if there is I have a minus sign here, a minus sign if there is a plus, or no sign. If there is a minus sign, I have here a plus sign, followed by the product of the functions in the loop. If you go one time through the loop, here you have the list of all blocks you can find. Yeah? So the forward block, we say the forward block divided by division line 1, opposite sign as the feedback signal, multiplied with all blocks in the loop. That is the feedback rule of block signal block diagram reduction method. Let's apply these 3 rules to our previous signal block diagrams. For example, here the signal block diagram of my not inverting amplifier, isolation amplifier. This I make a quick copy and then I apply this. There is an input voltage U1, then we have block function V, output U2, and a summing point here with negative feedback. Yeah, that was this circuit. UD is not interesting, just a negative feedback output to the summing point of the input. Here this directly can be combined. F nu is voltage gain U2 over U1 is what? This is a feedback structure. Very simple to this. Only F2 is missing. It's not missing. F2 is just a line. And if you have no F2 in this line, then F2 is 1. Yeah, here you can say here F2 is 1, F1 is V. So we can directly write down the resulting function is forward block from U1 to U2 is V, feedback block is 1, and the denominator starts with a 1, always with a 1. If you have a feedback, you have a division line with a 1 in the denominator, followed by the opposite of the feedback sign. The feedback sign here is a minus sign, so we have to follow with the plus sign, and now followed by all blocks in the loop. There is only one block, this is my V, the F2 is 1, so this is the voltage gain of our inverting amplifier with approximation number 1. With approximation 1, V goes to infinity. What is the resulting transfer function? Fn is infinity divided by 1 plus infinity. I can divide both numerator and denominator with V, then this is 1 over V is, this is a 1, this is a 1, this is 1 over V goes to 0, so this is 1. So the voltage gain of this circuit is 1 if the differential amplification factor, the differential gain is infinity. Yeah. With approximation 2, what we get is this: Fn is V0 divided by 1 plus V0, and if V0 is the the guaranteed gain of the MU-A741, which is 20,000, then you see, okay, this is nearly 1, but not exactly 1. This is, if I put it into my calculator, a little bit smaller than 1. That is, I think, 3/9 and then a 5. Yeah. So this is nearly 1, but not exactly 1. If you want to use this circuit as an input amplifier in a 6-digit voltmeter, then you should check if the accuracy good enough. If you have a 6-digit voltage meter, then of course you can see 4 digits are okay, but the 5th digit is wrong. So then you should look for an operation amplifier which guarantees, I think, 1 million as a smallest DC gain value. Okay, that's an example application for this circuit. Let's look for another application. Yeah, I think what is with this circuit? Yeah. If I go back to the, I think that this, let's do this. Simple single order low pass filter. Here we have a circuit. I just make a copy and copy paste. Yeah, copy paste of this circuit. I just have copied this picture and passed here at this position. I want to have the goal. I want to have U2 over U1. So this should be converted into one block. First, okay, what is this? This combination here. This combination is a series connection. This PC is followed by this R block, and I easily can put these blocks together in a block with a new function. Yeah, these two blocks becomes one block with which function? The product of the both functions. So this is P times C times R. This is the first rule applied to my circuit, and then you see this is a simple feedback rule. Feedback. I can say, okay, F new as a voltage gain, U2 over U1 is, feedback rule is a division line with a 1 in the denominator. Always this is fixed. If I detect feedback structure, then this is the first step what I can write down. The direct connection from input to output. It has no block. No block means a 1 in the function. Yeah, no block means input is output, and this is the ratio of input and output if both are equal is 1. So this is a 1 divided by 1 followed by the inverse of the feedback sign. The feedback sign is negative, so I have here positive sign, followed by all blocks in the loop. There are no blocks, and here is just this block. So I just have to write here a P times C times R, and this is a new function, and the product of a capacitance with a resistance is a time. So this is a time constant of the system, is a product C times R. Okay, this is a simple application where we use the series connection rule and the feedback rule, and now I want to show you that we have not enough rules. We need more rules. This will be shown in the example with the two RC blocks connected. Yeah, where is the circuit? Moment, let's write here. Here we have the signal block diagram of the RC-RC connection. Here you see a structure where overall there is a feedback, but then we have here internal connections in that way. Internal connections in that way means, if I look for this feedback rule, I cannot put it together with a simple equation, because these connections then now are disturbing this rule. So I cannot apply this rule directly. The same as with, what is this? Is this a parallel structure? No. What is this? Is this a parallel structure? Not really. So at this time, with my 3 rules which I have started, I cannot continue. It is impossible to put this structure into one single block. With these 3 rules I need more rules, and I will show you in the next video which tricks I can use to have the complete transfer function in one block in this application. Yeah, next video.